Hi, my name is Rodolfo Hasso Campos, and today we'll explain the experiment of the pressure-depth relationship. Okay, so first of all we need to see this formula. This is that the change of pressure is equal to the density of the fluid times the constant acceleration times the change in height. So what this means is, for example, for a pool full of water, that the deeper you go, there will be more pressure as both the density and the gravitational acceleration stay roughly constant. So therefore we can change this formula in order to put that instead of a change of pressure, the absolute pressure will be equal at any point to P0, which will be the ambient pressure, which will be, for example, a point right here, which, for example, in this case is the pressure of the air, plus the density of the fluid, in this case water, times the gravitational acceleration, times h will be the height to that point. For example, a point right here on this pool, this distance right here will be h. But this formula only works if the liquid is static. But right now we need to see what happens when a liquid is dynamic, it moves. So for example, we have this case in which a liquid not only moves, but also changes the area of which it's moving. And what I mean by the area is this average right here. For example, here you can see the tube has a higher area, while this part of the tube has a much smaller area. And this also changes the velocity of which the liquid flows. So how can we calculate this? Well, we need to make an assumption that this liquid will be perfect. What this means is four things. One, that this liquid is laminar. Therefore, any point, for example, this one right here, will have a certain velocity. And the velocity will not change over time. Secondly, that it's incompressible. Therefore, the liquid doesn't change density. Third, that the liquid is non-viscous. Therefore, there is no interaction between its particles. And fourth, that the liquid is not rotating. With all these assumptions, we can then make this formula. This says that the change of volume, which will be an area, for example, area 1, times delta x1, which will be this small distance right here, delta x1, will be the same as a volume right here, which will be A2 times a delta x2. Now, why these volumes are the same is because, again, the liquid is incompressible. So therefore, we need to see what happens to change to the same amount of water in a volume in one part of the tube compared to another. So we see that these two volumes are the same. But then we can replace this delta x with the relationship between velocity, distance, and time by saying that it's equal to its velocity, for example, velocity 1, times the change of time. We are saying that the change of time is the same for this volume than this one. This is because it's incompressible. So therefore, we can replace in the formula this, and we get the following formula. The change of volume is equal to area times velocity times the change of time. And this equation does not change as they are the same. But then we can divide everything by the change of time, and we get that the change of volume divided by the change of time is equal to the area times the velocity of each of these parts. Okay, so how we're going to get to Bernoulli's equation, which is how we're going to what this one bases on, is we're going to then use the equation for the conservation of energy. As you know, a small change in the work is equal to a small change in the kinetic energy plus a small change in the potential energy. So for example, we have this water or liquid flowing through this tube. As you can see, there are a lot of variables. Here we have, again, its area of a part of the tube, which is different on both. The small distance that makes the small volume in both parts. Then it's important it's small distance in order to make this approximately similar. As it changes from here to there, it isn't perfect, but the smaller the distance, the more perfect cylinder it will be. We also have pressure times the area, which in other words is the force, which is pushing right here, and the force pushing on the other way. well as the velocity, which keeps the liquid flowing from point A to B, or from here from point C to D. As well as there is a difference in height. Here is at y1, here is at y2. So assuming, as the energy conserves and seeing this mock-up, then we can do some things. For example, that they work ignoring any force because it is a perfect liquid, therefore there's no force between them, and we ignore gravity. We can say that is equal to the change of pressure from one point to the other times the change of volume. This because this pressure is what makes the liquid move. For example, a point right here, it's only moving, the liquid right there will move because of the pressure exerted from this way. But it will go against a pressure exerted from this way. And the flow depends on which of these pressures wins. But we can say this is equal to the difference of pressures. Then for the kinetic energy, you can just use the formula for kinetic energy, that is half times the mass times the velocity squared. But in this case, mass, we can represent it by the density times the change in volume. As well as the velocity squared will be the change in velocity, we're using the change in kinetic energy. And finally, for the potential energy, we can use the formula for mass times the rotational acceleration times the height, and using the same things, making the mass become the density times the change in volume, as well as the difference in heights. Okay, so we replace all of these terms in this formula on the top. We get the following formula. It's somewhat complicated, but as you can see, we can cancel all of the small changes in volume, all of the small volume, sorry. And we get the next formula. Now from this, we can actually distribute for the changes in volume and changes in height. As you can see, the initial ones will be negative. So we can pass them to the other side positive, and this final pressure, we can pass it to the other side as well positive. So therefore, all of these terms will be positive. On the left, we have all the initial points, and on the right, we have all the final points. And they will be actually the same. So therefore, we can say that at any point in this flow, the pressure times half the density times the velocity squared, plus the density times the rotational acceleration times the height is always constant. This doesn't change in any of these points. Now this is Bernoulli's equation. Now what we're going to do for this experiment is try to prove this equation. How we're going to do it is we're going to make this experiment right here. As you can see here, we have a bottle with 3 little holes in it, as well as 3 measuring tapes on the bottom. Now what we're going to try to do is use Bernoulli's equation in order to get both in order to get the distance of as you can see here at the top, this part is open, so this is the temperature at minimum pressure. But if we make this water right here and we pop one of these things, the water will eject it at some velocity. It's because here is a change of area, and as we saw, a change of area means a change in velocity. So therefore, it will be launched with some velocity and land somewhere in here, and this will be a range. What we're going to try to do is know what the theoretical range will be and compare it to the experimental range. So first of all, to do this, we get Bernoulli's equation, and as you remember, all the initial parts are on the left and all the final parts are on the right. Now for the initial part, as you can see, the pressure is just the ambient pressure, which is right here. The next term with velocity, we're going to assume is 0. This because the velocity at which this water will start to go down, because of this launch of the water, will be much smaller because it is a much smaller area right here. So therefore we can assume it's negligible, so we just don't consider that term. Then for the final term will be the density of the water times the concentration times h. H is in this case the level of water, which is this distance right here. This is h. For the final part of this equation, we have as well the ambient temperature, therefore these two can be cancelled out. here we do consider the velocity, which is this one right here, which will be squared times the density of water divided by 2 plus the density of water times the constant of extension times h. H will be the height at which this hole is, which will be this one. Then we can, as I said, cancel the ambient temperatures and pass this term right here to this term right here and factorize the density of water and the gravity. So therefore, it's the density of water times the gravity times the height of the water minus the height of the hole will be equal to the density of water times the velocity squared divided by 2. Here you can see both densities are cancelled. Then we can pass the 2 multiplying and take the square root, and we get this formula here. The square root of 2 times the acceleration of gravity times the height of the water minus the height of the hole, all of that square rooted is equal to the velocity. I should say that we're going to see water because water roughly is close to what we said was an ideal fluid. It's really incompressible and it's very non-viscous, etc. Okay, so then when we have this formula for velocity, then we're going to try to get this velocity, the range, the distance, which remember is the distance right here, at which the water will topple down, like this. So from the parabolic motion this will make, we can therefore note that this distance will be equal to the velocity, initial velocity, times the square root of 2 times the height of this hole, which will be in this case lowercase h, divided by the gravitational acceleration. Then we can replace the velocity with the one formula we got before, and get this formula. As you can see, 2 times 2 makes 4, and we can factorize it from the square root. We just get that 2. The gravitational acceleration, we cancel each other, and we just multiply by h. So therefore, we get that this range will be equal to 2 times the square root of the height of the hole times the height of the water. Remember, this thing right here is uppercase h minus the distance from the hole. Now, why we have 3 holes is because we're going to try to do a lot of points using this formula. So therefore, we're going, as the water is lowering, now we're going to pop this one, and when it is the height of water will be below, then we're going to pop the second and third one, etc. So therefore, we can get a lot of data points. Here you can see it has some markings, this bottle of water, in order to know the level of the water at any point. Okay, so what we did was get these points and compare them theoretically with the formula we just saw and the experimental distance you got from the measuring things. And in theory, this should be a perfect relationship, which, as you can see, it's very close. As you can see, the slope is 0.9 plus 0.25, and we actually want to get 1. And as you can see, it's in this range. As for the distance from the origin, we got about 0.6, and the ideal one should be 0. So you can see we got a pretty close relationship, therefore proving that the formula for Bernoulli's equation, it actually works. As you saw, we got these results from the derivation of that formula. And all of these assumptions actually made sense, and therefore we got a pretty accurate result. One thing to add is that, as you saw before, the distance cancels the gravitational acceleration as well as the density. So as long as you're using a perfect fluid, no matter if it's water, no matter in which planet you make experiments, it could be on Earth, it could be on Mars, for example, the range will be always the same, as the gravitational acceleration doesn't matter. This can be seen as, because the velocity does matter of the gravitational acceleration, as you see right here, the velocity will be lower on a lower gravitational field, for example in Mars, but as there is lower gravity, this smaller velocity will not affect the range, as it can go further without falling immediately to the ground. So therefore, the range actually stays the same. Thank you for